Testing regression errors for normality. One of the assumptions of classical linear regression model is that errors are normally distributed. This lecture is devoted to test this normality assumption on some real-world data. It is important to note that true errors, like true regression parameters, are unknown and unobserved. So normality of true errors cannot be established. Hence, this assumption is generally tested on OLS residuals which are observed, and they can be calculated based upon some sample data. A normal distribution has many features. First one, it is unimodal with a bell-shaped center. So here it has only one mode with the center at 0. It is symmetric around the mean. The mean is 0 in this case. We can see that the shape on the left of this 0 is same as the shape on the right of the 0. So this indicates the symmetric property, and this line is called line of symmetry or axis of symmetry. Its tails are exponentially declining, so this is called the left tail, this one is called right tail. We can see that the tails are declining at a very fast rate. Several tests are available in literature to test a data series for normality. It is emphasized that different tests are good at detecting different types of departures from normality. In this lecture, we are going to discuss many such tests. Key approaches to test for normality. Two main approaches are used in literature. The first one is called informal method, also called graphical method, such as plotting a histogram of the OLS residuals or any other data series, and also making a normal probability plot. The second method is called formal method, where we use some proper statistical or econometric test. Some of the famous tests that are used in literature to test a data series for normality are skewness and the kurtosis measures, the Jarque-Bera test of normality, and Kolmogorov-Smirnov test, among many others. Let's discuss these two methods one by one. So let's first discuss the informal method, histogram of OLS residuals. This method involves constructing an histogram of OLS residuals and seeing if it matches with the bell-shaped normal curve drawn with the same mean and same standard deviation as that of OLS residuals. This means that we need to calculate mean and standard deviation of OLS residuals, and then from the mean and standard deviation we can calculate this bell-shaped normal curve. Because normal distribution has two parameters, mean and variance, we have calculated the mean from OLS residuals as well as standard deviation. The square of standard deviation is variance, so we have two parameters with us. So once we have these two parameters in hand, we can construct a normal density curve, and then we can match the histogram of OLS residuals with this normal density curve. If there is a good match, then the OLS residuals are said to be normally distributed, otherwise not. This figure shows OLS residuals histogram with normal curve with same mean and same standard deviation as that of OLS residuals. The red line is the normal curve with mean equals to mean of OLS residuals and standard deviation equal to standard deviation of OLS residuals. And the histogram is represented by these blue bars. Roughly speaking, there is a good match between the residuals histogram and normal density curve. However, there is slight mismatch at this peak. The peak of histogram is somewhat higher than the peak of normal curve. The right hand side also shows some mismatch, but overall there is a good match between the two. Let's discuss the second informal method, normal probability plot. This method involves comparing observed cumulative distribution function, the CDF of data series or OLS residuals in our case, with the theoretical CDF of standard normal density with matching mean and standard deviation as that of OLS residuals. If the CDF of OLS residuals, which is also called observed CDF, matches with the CDF of normal, which is also called theoretical CDF, so if there is a match between observed and theoretical CDF, then the OLS residuals are said to be normally distributed, otherwise not. Figure shows observed CDF of OLS residuals versus theoretical CDF of normal with matching mean and standard deviation as that of OLS residuals. So this red line gives us theoretical CDF of normal with mean 0 because the residual series has mean 0, and the second component is the variance, which is square of standard deviation. And this blue line gives the observed CDF of OLS residuals. From this figure we can see that there is a good match between the two, although there is some discrepancy in the center, but overall a good match. So from this normal probability plot we can conclude that the residual series is normally distributed. So we have discussed the two informal methods. Now let's move to the formal method. The first one is using skewness measure. Since normal distribution is symmetric, that is equally spreaded around the mean, so one measure of assessing residuals for normality is to see if they are symmetric or not. Here in this diagram, 0 is the mean, and we can see that area to the left of the mean is same as area to the right of the mean, and the shape to the left of the mean, this 0 line, is same as shape to the right of this zero line. So the normal distribution, this bell-shaped curve, it is symmetric, so equally spreaded around the mean. To assess lack of symmetry, skewness measure is used. In this diagram we can see that the middle one is the normal distribution with no skewness. Here in this diagram we can see that the right tail is longer than the left tail, so it means there is asymmetry. Both tails are not equal in length. So this is the situation of positively skewed distribution or right skewed distribution, because right tail is longer than the left one. In this diagram the left tail is longer than the right tail, so this is called negatively skewed or left skewed. For normal distribution the value of skewness is 0. Theoretically this value is 0, but for sample data this value can be slightly different from 0. But as sample size increases, the value of skewness will converge to 0. Calculations of skewness measure. How skewness can be calculated? Let x be a random variable with mean mu and variance sigma square. Then skewness is defined as expected value of x minus mu over sigma whole cube, which is also called third standardized movement. Please note that mu is being subtracted from x, so it means x is being centered here, and then this difference is being divided by sigma, so it means the x is scaled as well, so x is centered as well as scaled, so it means x is made standardized, and then the third power of this, and then the expected value, so it is called third standardized movement. Let's demonstrate how we can calculate skewness measure for some hypothetical data using MS Excel. Let x be a random variable containing 4 values 1, 2, 3, 4. First step is to calculate average of these 4 values, the mean, and next step is to calculate standard deviation of these 4 values. The mean is found to be 2.5 and the standard deviation is found to be 1.118. Next column, standardize this x variable by subtracting mean from each value of x and dividing this difference with the standard deviation. Name this column as z. So from this first value of x, 1, subtract the mean which is 2.5, so 1 minus 2.5 which is minus 1.5, and divide this minus 1.5 with this standard deviation 1.118. The answer is minus 1.342. And similarly 2 minus mean over standard deviation, 3 minus mean over standard deviation, 4 minus mean over standard deviation. Excel command to get result in this column is given here. So B2 minus B6 divided by B7. So B6 is the average value and whole divided by B7. B7 is the standard deviation. And I have used the dollar signs to fix both mean and standard deviation. Copy this command downward. B2 will change to B3 and then B4 and then B5. But B6 and B7 will remain fixed due to dollar signs used. And then in the next column take cube of all these values. So C2 cube, C3 cube and so on. And finally take the average of these 4 values. The average is 0. So this average is called the skewness. So this is how you can calculate skewness. In Excel you can use skew command to calculate skewness. Put an equal sign and type skew, and then within the parenthesis your data series range. In our case the data lies in cell B2 to B5. B2 is the first value and B5 is the last value. If skewness is 0, then the distribution is symmetric, the one shown in the middle. If skewness is greater than 0, then the distribution is right skewed, the one showed here, positively skewed or right skewed. If skewness is less than 0, then the distribution is left skewed, this one negatively skewed or left skewed. Now let's discuss the second formal method, which is kurtosis measure. Another way to assess normality is to see if tails or peak of the distribution of OLS residuals match with the tails or peak of the normal distribution with same mean and same standard deviation as that of OLS residuals. This is done by using kurtosis measure. For normal distribution, kurtosis is 3. Now let's discuss how we can calculate kurtosis measure. Let x be a random variable with mean mu and variance sigma square, then kurtosis is equal to expected value of x minus mu over sigma whole raised to power 4, and it is also called the fourth standardized movement. Let's discuss how we can calculate kurtosis using MS Excel. Take the same x variable containing 4 values 1, 2, 3, 4, calculate the mean which is the average, calculate the standard deviation, and then in the next column calculate the standardized variable, the same z variable, by subtracting mean from each x value and dividing this difference with the standard deviation, and finally calculate the fourth power of this variable z and take the average of these 4 values to get the value of kurtosis. So here is the command, average command to calculate this mean, and stdev.p is the command to calculate standard deviation, and then the usual command to calculate the standardized variable z, and now c2 raised to power 4 to calculate the fourth power, and finally we took the average to calculate the value of kurtosis. Kurtosis in our case is 1.64. If kurtosis is equal to 3, then the distribution is mesokurtic or normal. So here the red one. If kurtosis is greater than 3, then the distribution is leptokurtic, the blue one. If kurtosis is less than 3, then the distribution is platecultic, the green one. There is an alternative measure of kurtosis as well, that is called excess kurtosis, E for excess, K for kurtosis. Excess kurtosis can be calculated by subtracting 3 from kurtosis. Ek is equal to kurtosis minus 3. In Excel, you can use kurt command to calculate excess kurtosis. Equal sign KURT B2 to B5. So this command will calculate excess kurtosis of the values containing in cells B2 to B5. Please note that there is no command in Excel to calculate kurtosis directly. However, you can use excess kurtosis formula to calculate the value of kurtosis. This is done by this formula: kurtosis is equal to excess kurtosis plus 3. This is obtained by shifting this minus 3 to the left hand side. So 3 is being subtracted here. When it is shifted to the left hand side, it gets added to excess kurtosis. So kurtosis is equal to excess kurtosis plus 3. Now it is easy to verify that for normal distribution or mesokurtic distribution, the value of excess kurtosis is 0. For leptokurtic distribution, the value of excess kurtosis is greater than 0. And for platecultic distribution, the value of excess kurtosis is less than 0. So let's discuss the summary of skewness and kurtosis measures. To test OLS residuals or any other data series for normality, calculate skewness measure as well as kurtosis measure. If skewness is 0 or close to 0, then the distribution is symmetric. If kurtosis is 3 or close to 3, or excess kurtosis is 0 or close to 0, then the tails of the distribution of OLS residuals match with the tails of the normal distribution. This implies that the distribution of OLS residuals is normal. However, if any of the skewness measure or excess kurtosis measure is different from 0 or kurtosis is different from 3, then the distribution of OLS residuals will be non-normal. So for normality, skewness must be 0 or close to 0 and kurtosis must be 3 or close to 3. Or in other words, excess kurtosis must be 0 or close to 0. If skewness is 0 but kurtosis is different from 3, then it means the distribution is symmetric, but the tails of the distribution of OLS residuals are not matching with the tails of the normal distribution, which is also called the benchmark distribution. If skewness is different from 0 but kurtosis is 3, then it means the distribution is asymmetric, not equally spread around the mean, but the tails of the distribution of OLS residuals are matching with the tails of the normal distribution. Please note that for normality, the skewness must be 0 and kurtosis must be 3. If any of these two measures differs from its benchmark value, 0 in case of skewness and 3 in case of kurtosis, then the distribution will not be normal. So for normal distribution, skewness must be 0 and kurtosis must be 3, or excess kurtosis must be 0. Please note that in case of sample data, the value of skewness can be close to 0. It may not be exactly 0. Similarly, the value of excess kurtosis will be close to 0 and it may not be exactly 0. And the same holds true for the value of kurtosis, which will be not exactly equal to 3, but it will be close to 3. Let's move to the third formal method, the Jarque-Bera JRB test. Instead of testing normality using individual skewness and kurtosis tests, Jarque and Bera proposed a combined test known as Jarque-Bera or JRB test. The null hypothesis of JRB is OLS residuals are normally distributed, and the alternative hypothesis is OLS residuals are not normally distributed. This null hypothesis is tested via JRB statistic, which is given by this formula. JRB is equal to T times skewness square over 6 plus excess kurtosis, which is kurtosis minus 3 whole square over 24, where skew is the skewness measure, kurt is the kurtosis measure, and T is the total number of observations. Please note that instead of kurtosis minus 3, you can simply add EK, which is excess kurtosis. So in different books, you may see that version of the formula. JRB statistic follows chi-square distribution with 2 degrees of freedom asymptotically. Asymptotically means only in large samples. Its critical value can be found via critical value table of chi-square distribution, which is usually available in the appendix of most of the statistics and econometrics textbooks, or you can use Excel command as well. So put an equal sign and then type chi inv inverse. So chi inverse and within parenthesis alpha, where alpha is the significance level, which is usually taken as 1% or 5% or 10%. So 1, 5 and 10% are called conventional significance levels, and this df is called degrees of freedom, and degrees of freedom is fixed at 2. For alpha equal to 5% and degrees of freedom equals 2, which is fixed, critical value is calculated as equal sign chi, I and V, and within parenthesis 5%, which is 0.05, and comma 2. 2 is the degrees of freedom. Now let's discuss the decision about rejection or non-rejection of null hypothesis. If JB calculated is greater than critical value, it means the calculated value of JB statistics calculated via formula that is shown in the previous slide is found to be greater than the critical value which is obtained via this command. Then we reject the null hypothesis at 5% significance level because this critical value is calculated at 5% significance level. So please note that whenever we reject a null hypothesis, we need to mention the significance level, that at what significance level this null is being rejected. Currently we have calculated the critical value at 5%. That's why we are mentioning that reject null hypothesis at 5% significance level. But if the critical value is suppose calculated at 1% instead of 0.05, suppose you have used 0.01, and if JB calculated is found to be greater than 1% critical value, then reject the null hypothesis at 1% significance level and conclude that OLS residuals are non-normal. So it's up to you which significance level you use. So generally all these three significance levels are used: 1%, 5% and 10%. And if JB calculated is found to be less than critical value, then do not reject null hypothesis at 5% significance level and conclude that OLS residuals are normally distributed. Instead of using the critical value and comparing the calculated value of JB statistic with the corresponding critical value, one can also use the p-value method to test the validity of null hypothesis. Excel command for calculating p-value is equal sign chi dist and within parenthesis calculated value of JB statistic, which will be calculated via formula shown in the previous slide, and comma df, where df is equal to 2 fixed, which is the degrees of freedom. Now let's discuss the decision regarding rejection or non-rejection of null hypothesis using this p-value method. If p-value is less than significance level, 1% or 5% or 10%, then reject the null hypothesis of normality at chosen significance level, 1% or 5% or 10%. Suppose here you have selected 1%. So then if the calculated p-value calculated via this command is found to be less than 1%, 0.01, then we will reject the null hypothesis of normality at 1% significance level. And if suppose calculated value of p calculated via this command is found to be less than 0.05 or 5%, then we reject the null hypothesis of normality at 5% significance level. Similarly, if the calculated p-value calculated via this command is found to be less than 10% or 0.10, then we reject the null hypothesis of normality at 10% significance level, and we conclude that OLS residuals are non-normal. And if p-value is greater than significance level, 1% or 5% or 10%, then do not reject the null hypothesis of normality at chosen significance level, 1% or 5% or 10%, and we will conclude that OLS residuals are normally distributed. So this is how the decision regarding rejection or non-rejection of null hypothesis is taken using p-value method. Let's discuss an important note on critical value of JB statistic. Since JB statistic has chi-square distribution with 2 degrees of freedom asymptotically, this means that the distribution of JB statistic is valid only in large samples, implying that when sample size is small, then the distribution of JB statistic may not be chi-square, but it may be some other non-standard distribution other than chi-square. This means that the critical values and the p-values calculated previously based on asymptotic distribution, which is chi-square, they may not hold true in small samples. And the conclusion regarding rejection or non-rejection of null hypothesis may be misleading in finite or small samples. Please note that the concept of large sample is subjective. In some cases, a sample of 100 observations will be considered as large, and in some other cases, a sample of even 1000 observations will not be considered as a large sample. Generally, it is advised not to use critical values based upon asymptotic distribution. So how to overcome this issue of finding critical values in finite samples or small samples? This can be done by calculating a new set of critical values at 1%, 5% and 10% significance levels for small samples by carrying out simulations. The process of carrying out simulation is explained in the empirical example and the Excel demonstration in forthcoming slides. Let's demonstrate all this with the help of an empirical example. Consider a multiple linear regression model relating composite SAT score CSAT with the percentage of students who appear in the SAT exam percent and expenditure per pupil by the government expense. The data consists of 51 states of US, and here is the multiple linear regression model where CSAT is the dependent variable, percent and expense are two independent variables, epsilon is an error term, and beta 1, beta 2, beta 3 are regression coefficients, and the sample contains 51 observations. Our objective is to estimate this multiple linear regression model via ordinary least square method, the OLS, and test the residuals obtained from this regression model for normality using all methods discussed in this lecture. Specifically, we will focus on the two informal methods and the two formal methods that we have discussed. So first one is constructing histogram of OLS residuals and matching it with the bell-shaped normal density. The second one is by constructing normal probability plot, and the third one is skewness and kurtosis measures, and the fourth one is the Jarque-Bera or JRB test. So let's move to the Excel sheet for demonstration. Here in Excel spreadsheet we have data on dependent variable CSAT and independent variable percent and expense. The data ranges from row number 2 up to row number 52, so it means total 51 data points on each of three variables. And our objective is to estimate this multiple linear regression model where CSAT is dependent variable and percent and expense are two independent variables. This can be done using data analysis toolpack. Go to data tab, and here on the top right corner click on this data analysis button or tab. Here in the data analysis dialog box, choose regression. So select this regression, click on OK. And now in this regression dialog box in input Y range, select this CSAT variable including this column heading. So A1 up to A52. And then in the input X range, select both variables percent and expense. So click on this arrow. And now select these two variables B1 to C52. Since we have also selected the column headings or column names, so check this box labels. Now in the output range, provide any blank cell, E7. And finally check this box of residuals as well. Click on OK button. Here is the output. R square is 78%. All variables are significant at 5% significance level. We are interested in this residuals output. So please note that here are the residuals. Now our objective is to test these residuals for normality. That is whether they are normally distributed or not. First method that I am going to do is to construct the histogram of these residuals, and then I will try to match it with the bell-shaped normal curve with the same mean and same standard deviation as that of residuals. In order to construct histogram, I am going to calculate the minimum value of residuals and maximum value of residuals first. So min command is used to calculate the minimum value. So minimum is minus 62.9. Calculate the max value. So max of residuals 75.62. Calculate the range, which is the difference between max and min. So max minus min. Next, how many bins for the histogram are required? So number of bins, suppose 10, and class interval. This is range divided by number of bins. Now construct bins starting at minimum value and going up to maximum value. So bins, put an equal sign and get the minimum value pasted here, and then put an equal sign this minimum plus this class interval. Use dollar signs to fix it. Select it and copy this command downward. And here this last one is the max value. In the next column, I am going to calculate the frequency. Select this whole column, put an equal sign and type frequency. Then first argument is data array. Data array are the residuals. Use dollar signs to fix it. Press Fn key from your keyboard and keep pressing it down, and then press F4. This is the shortcut to use dollar signs. Comma, then the bins array. For bins, select this range. Close the parenthesis and now press Ctrl Shift Enter simultaneously. So here we have obtained the frequencies corresponding to each bin. Select both columns, go to Insert tab, choose this Scatter and choose this Connected. And now click on this graph, right click, change series chart type, and here select columns. Click on OK. This is the histogram of these residuals. If you want to reduce the gap between the bars, right click on the bar, choose Format Data Series, and here gap width, it is currently 150%. Reduce it to 0%. And now in the color option, in the border, select solid line and change its color to white and increase its width to 2 points. And here is our histogram. Move this chart to a new sheet. Right click, select move chart, new sheet and chart 3. OK. Now our objective is to draw a bell-shaped curve on this histogram. Again move to sheet 5, our working sheet. For this we need to calculate mean and standard deviation of these residuals. Type here mean and then the standard deviation. So mean is the average. By the way, by construction the mean should be 0 because sum of residuals is 0. So mean is 0 e minus 14, it means 0.0013 times 0 and then 445, which is approximately 0. And then standard deviation stdev dot p, p for population. Select this and press enter. So we have calculated the mean and standard deviation. Since normal distribution has 99.7% of the probability that lies in the interval mean minus 3 standard deviation and mean plus 3 standard deviation. So first I am going to calculate these two limits. So here mean minus 3 times standard deviation and then mean plus 3 times standard deviation. So put an equal sign, mean is this value minus 3 steric for multiplication and then standard deviation and then mean again plus 3 times standard deviation. So now I am going to construct a variable x ranging between this mean minus 3 times standard deviation and mean plus 3 times standard deviation, that is from minus 92 to plus 92. So here in this cell I am going to construct a number of bins. So number of bins 100, you can even choose 200 or 400 or even 1000. The larger the number of bins, the more smooth will be the normal density curve. And here I am going to add a step size. Step size can be calculated by taking the difference of mean minus 3 standard deviation and mean plus 3 standard deviation and dividing this difference by number of bins. So equal sign, mean plus 3 standard deviation minus mean minus 3 standard deviation slash number of bins 100. Press enter. So 1.84. Smaller the step size, the smoother will be the normal density curve. So here if you select 200, so we get 0.92, which is smaller than the previous step size of 1.84. So the smaller the step size, the smoother will be the curve. I am keeping the number of bins to 100. In this cell construct the variable x containing values between mean minus 3 standard deviation and mean plus 3 standard deviation with the step size of 1.84. The first value is this mean minus 3 standard deviation. In the next cell put an equal sign, choose this previous value plus this step size and use $sign to fix this step size. Copy this command downward till we reach at this value mean plus 3 times standard deviation, which is plus 92.03. So in our case it occurs at row number 131, so 92.03. So now we have generated the x values. In next column calculate the probability density function of normal distribution with mean 0 and variance equal to the square of this standard deviation 30.678. Type here f of x and use norm.dist command. First argument is x, which is located here, and then comma mean, which is 0, and then comma standard deviation, which is located here in this cell. Use $sign to fix it, and then cumulative false. So this gives the probability density function of a random variable x which follows normal distribution with mean 0 and standard deviation this 30.678 for this first value of x minus 92.03. Please note that the value of probability density function is unscaled, so we need to adjust its scale. This can be done by multiplying this value of probability density function with total number of sample points, which are 51 in our case. So multiply this with 51. Put a asterisk sign at the end and then type 51, and then you need to multiply it further with this class interval, which was the class interval of this residuals histogram. So use this cell address as well, J35. So we actually multiplied this probability density function with total sample points 51 times the bin width of this histogram. Press enter. This is the value of probability density function after adjustment of scale. Click on this cell to copy this command downward. In order to obtain the bell-shaped curve, select both columns. Go to the Insert tab. In the scatter option, choose this smooth line. So this is the normal density curve. Now let's construct the histogram using the information in these two columns on this chart. This way we will get a histogram and the bell-shaped curve on the same graph, and then we will be able to compare the histogram with the bell-shaped curve, and we will see whether the residuals histogram matches with the bell-shaped normal density curve or not. In order to do this, right click on this chart, choose select data, click on this add button. In series name, select this frequency. Series X values, select the bin range starting from row number 1, not the column names. Series Y values, select the frequency value. Once you are done with it, click on OK button. Click on OK. So now on this graph we see the residuals density as well. The next task is to change the shape of this residuals density to a histogram. Please note that there is no direct way of converting this residuals density to a histogram in Excel. So I am going to use one simple trick here. Click on this residuals density, click on this chart design, and now add chart elements. Go to error bars, click on more error bars option, change the direction to minus, and style select no cap. In the percentage, change this 5 to 100%. Press enter. Now here is the graph. Next task is to increase the width of these error bars so that they look like bars of a histogram. Select the bars by clicking on them. You can see that the bars have been selected. Click on this fill and line. Now increase this width from 0.75 to suppose 13. Now you can see that the width of the bars got increased. The final point is to get rid of this brown curve. Click on it and select no line. So this has been removed. So here is the graph. We have the residuals histogram and we have the bell-shaped curve over it. We can see that the peak of the residual histogram is lying above the normal density curve, and also the right tail probability of histogram is somewhat higher than the right tail probability of normal density curve. Roughly we see a good match between the two, but we need to confirm it using some proper statistical tests. This completes our first task, comparing residuals histogram with normal density curve with same mean and same standard deviation as that of residuals. Let's move this chart to a new sheet. Right click, select move chart, new sheet, click on OK. Our next task is to draw a normal probability plot. Select these residuals, copy them, Ctrl C, and paste them here, Ctrl V. Now arrange these residuals in ascending order from lower to higher value. Select these residuals. In the data tab, click on this sort button. Sort by residuals and order smallest to largest in ascending order, lower to higher. Click on OK. This gives sorted residual series. In next column, I am going to calculate the cumulative distribution function of these residuals. That is called observed CDF of these residuals. Luckily in Excel we have the command to calculate cumulative distribution function of any data series. Put an equal sign and use %rank. Now it is asking me to provide array. Array is your residual series. Select this full range. Use $signs to fix it. Put a comma. And then this X is the first value of residual. There is no need to provide this information and significance. This is optional. Close the parenthesis and press enter. Double click to copy it downward. This next column I am going to calculate the cumulative distribution function or CDF of normal random variable with mean 0 and standard deviation equal to this 30.67, which is the standard deviation of residual series. I am naming this CDF as theoretical CDF. Theoretical CDF of normal with mean 0 and variance standard deviation square, where standard deviation is this number 30.6784. We have the Excel command to calculate the theoretical CDF of normal with any given mean and given standard deviation. Put an equal sign and type norm.dist, parenthesis, x value is the residual series, comma mean is 0, and standard deviation, choose this cell. P32, use $sign to fix it, put a comma sign, and for cumulative, yes, we need cumulative because CDF means the cumulative distribution function. Write true. Close the parenthesis, press enter, and now copy this command downward. You can increase the width. Now we need to compare observed CDF of OLS residuals with theoretical CDF of normal with mean and standard deviation same as that of OLS residuals. I'm going to use one simple trick to compare these two. Copy this theoretical CDF column, Ctrl C, right click on this cell and choose paste special and select this values radio button. Click on OK. You can see that the same column has been copied here. Next, copy the observed CDF of residuals. Select it, Ctrl C copy, and here in the next cell right click and choose paste special. Select values, click on OK button. So now you can see that we have three columns here. The first one is the theoretical CDF of normal, the next one is the same column theoretical CDF of normal, and third one is observed CDF of residuals. I'm going to select these three columns and I'm going to make a scatter plot of these three. Please note that Excel takes the first column along x-axis and the next two columns will be taken along y-axis. Look at the first two columns, they are exactly the same, so we will get a 45-degree line. And the values of this third column can be compared with this 45-degree line. So select these three columns, go to Insert tab, choose this scatter option and choose this one. So here is the graph. This graph is called normal probability plot. The blue line is the theoretical CDF of normal with mean 0 and standard deviation equal to the standard deviation of OLS residuals. And this brown line is the observed CDF of residuals. From this normal probability plot, we can see that there is a mismatch here on this side as well as on this portion of the graph, whereas on the upper tail and on the lower tail, there is a good match. Roughly, the observed CDF is matching with the theoretical CDF. Hence, on the basis of this graph, we can say that the residual series is normally distributed. So this completes the discussion of normal probability plot. Our third task is to use the skewness and kurtosis measures to assess the normality of OLS residuals. Here are the residuals, select them, Ctrl C copy and paste them here. I'm going to calculate skewness here. Excel command to calculate skewness is skew, put an equal sign and type skew, and within parentheses select these residuals, press enter. We can see that the calculated value of skewness is 0.348, and recall that the theoretical value of skewness under normal distribution is 0. So now we need to assess whether this 0.348 is significantly different from 0 or it is not significantly different from 0. If this 0.348 is significantly different from 0, then we will say that the skewness is positive and the distribution of residuals is right skewed. This can be assessed by comparing this calculated value of skewness with its critical value. This can be done by using simulations. Before carrying out simulation for the skewness measure, let's calculate the excess kurtosis and the kurtosis as well as the Jarque-Bera statistic, and then we will carry out simulations for all four. Here in this cell, I'm going to calculate excess kurtosis. The Excel command to calculate excess kurtosis is curt. So curt and select the residuals here. Press enter. So in order to assess whether the difference between 0, the theoretical value of excess kurtosis under normal distribution, and this calculated value or observed value of excess kurtosis, which is 0.17, is significant or not. If you want to calculate the kurtosis, recall that kurtosis can be obtained by adding 3 to the excess kurtosis. So excess kurtosis plus 3. So here this is the excess kurtosis, add 3 to it, plus 3, press enter. So the value of kurtosis is 3.17. Now question is whether this 3.17 is significantly different from 3 or not. If this 3.17 is found to be significantly different from 3, which is the theoretical value of kurtosis in case of normal, then we say that the peak of the distribution of OLS residuals is somewhat higher than the peak of the normal distribution. So here I have copied the formula of JRB statistics from lecture notes. Now I'm going to calculate this JRB statistic here. Equal sign, This t is 51, total number of observations, steric for multiplication, and then put a parenthesis. And now we need to type skewness square. Skewness is calculated here in this cell. So put a cap sign for square and write 2 divided by 6/6 plus kurtosis minus 3, which is excess kurtosis located here. Take square of this divided by 24. Close the parenthesis, press enter. So this is the calculated value of JB statistic. Recall that JB statistic follows chi-square distribution with 2 degrees freedom. So I'm going to calculate critical value at 1% and then critical value at 5% and critical value at 10% significance level. In order to calculate critical value at 1% significance level, the command is chi-inv and then the probability 0.01 for 1% and then degrees freedom is 2. Close the parenthesis and press enter. The critical value is 9.21. So critical value at 1% is 9.21. So here is the shape of chi-square distribution, and here we have 8 and 10. 9.1 will lie somewhat here. So put a vertical line here. So this is called the critical value. Area above this line is called the rejection region, and area below this line, this full region, is called non-rejection region. In our case, the calculated value of JB statistic is 1.09. 1.0 will be somewhat here. It falls in the non-rejection region, so we will not reject the null hypothesis of normality. So here I am adding the conclusion. Since JB calculated is 1.092, which is less than 1% critical value, so we do not reject null hypothesis of normality at 1% significance level, and conclude that the OLS residuals series is normally distributed. Now calculate the critical value at 5%. Put an equal sign chi inverse 0.05 now for 5% and degrees freedom is 2. The critical value is 5.99 or 6. Coming to this diagram, draw a line here. This whole region is called the rejection region and below this is called the non-rejection region. Calculated value of JB statistic is 1.09, which falls below this critical value, so we will not reject null hypothesis at 5% significance level, and we will conclude that OLS residuals are normally distributed at 5% significance level. Similarly, if you calculate the critical value at 10% significance level, type chi-inv 0.1 for 10%, comma, degrees freedom, which is 2. The critical value is 4.60. It will be somewhat here. So area above this 10% critical value is called rejection region, and area below this critical value is called non-rejection region. In our case, the calculated value is 1.092, which lies in this non-rejection region. So again, at 10% significance level, we do not reject null hypothesis of normality. These critical values have been calculated using chi-square distribution. And we know that JB statistic follows chi-square distribution only in large samples asymptotically. But here in our case we have only 51 data points. So question is whether the critical values obtained using this asymptotic chi-square distribution, they are valid when we have this small sample of 51 observations or not. Before moving to the simulations, let's discuss the p-value method of JB statistic as well. P-value can be obtained by using this Excel command chi dist. X is calculated value of JB statistic, which is located here, and degrees freedom is 2. Press enter. The calculated p-value of JB statistic is 0.579 or 57.9%. Now we need to compare this p-value with 1% significance level or 5% significance level or 10% significance level. In our case, p-value is 57.9%, which is not less than 1%. So we will not reject null hypothesis at 1% significance level. Also note that the p-value of 57.9% is not less than 5% significance level, 0.05. So we will not reject null hypothesis at 5% significance level. Similarly, the p-value is 57.9%, which is not less than 10% significance level. So we will not reject the null hypothesis at 10% significance level as well. Hence, the null hypothesis of normality is not being rejected at all three conventional significance levels, 1%, 5% and 10%. But here is a precautionary note. We have used the chi-square distribution to calculate the critical value and the p-value. Since our sample contains only 51 observations, so the question is whether JB statistic actually follows the chi-square distribution or not. If JB statistic doesn't follow chi-square distribution, then of course these critical values will be misleading.